So continuing our discussion of partitions, I want to make a strong case that you should think about partitions as diagrams as represented here. So one of the best ways to illustrate the point is to define the conjugate of a partition. Okay, it's going to be a new partition. It's usually denoted lambda prime. Okay, and I'll tell you what each part is. Lambda prime sub I is the number of j such that lambda I is bigger than or equal to, lambda j is bigger than or equal to I. Okay, so let's do an example. That's where we always want to start. So here's an example. I've got a partition for you right over here. It is 4, 3, 3, 3, 1. That is a perfectly good partition. It's a weakly decreasing sequence of positive integers. So let's follow this definition and try to figure out what is lambda prime. So what is lambda prime sub 1? Well, it's the number of lambda j's such that lambda j is at least 1. 1, 2, 3, 4, 5. It's 5. Sorry. Okay, what is lambda prime sub 2? It's the number of lambda j's that are at least 2. 1, 2, 3, 4 are at least 2. Okay? What's lambda 3 prime? So again, lambda j's, how many are bigger than or equal to 3? Same number, 4. What about lambda 4 prime? At least 4, one of them. And then the rest are going to be 0. So we're going to stop there and we're going to say, okay, based on this, I know what the conjugate is. So the conjugate is going to be lambda prime is equal to 5, 4, 4, 1. That's a rather tedious calculation to go through. If we think about lambda like this, okay, and you think about what this is actually saying, it's saying that you transpose the diagram and flip it like this. It's a little hard to see that red guy when you do it, so maybe I'll draw the pictures instead. So let's draw lambda. So this is my guy, lambda. It is 4, so we'll draw him with 4 bricks, and then a bunch of rows of 3 bricks. Wow, I'm going to need more bricks, and then 1 more brick at the top. Okay, so again, to emphasize, how am I thinking about this guy? Here is 4, 3, 3, 3, 1. What the conjugate actually does graphically is you take this main diagonal and you flip your diagram across that main diagonal. Okay, and then you're going to say, what is 5, 4, 4, 1? Well, if I draw that one, it looks exactly like this. So the row lengths here are 5, 4, 4, 1. But notice, those are the column lengths here, 5, 4, 4, 1. The columns here correspond to the rows down here. And conversely, if you conjugate twice, you get the same thing back. Is that obvious from the definition? Not to me, it's not, but maybe it is to you. But thinking about things graphically in this way helps us understand interesting operations that we can do on partitions, such as, for example, conjugation. Now let's think about another one that's going to be even more fun, which is I want to prove this theorem. This theorem doesn't exactly count the number of self-conjugate partitions, but it sort of does. So what does it mean to be self-conjugate? It means I'm equal to my own conjugate. So what's an example of a self-conjugate partition? Example would be 4, 3, 3, 1. How do I know that so easily? Well, let me actually work on that. How do I know that 4, 3, 3, 1 is self-conjugate? And I want to think about it without having to do too much work. So I'm going to get a bunch of parts. Okay, here are my parts. Okay, and I've got a part of length 4. So I'll start with that one. And I know that it's self-conjugate. So here's something I can do. I could just go ahead and stick another part of length 4 up top, because if it's 4 this way, if it's going to be self-conjugate, it's going to have to be 4 that way. That's fine. Now I need 3. But actually, I've already got this 4 here, so I'm just going to take one of these guys, because I just need to add 1 more. And I'm going to do the same trick, which is to sort of stack this guy here. Okay. So now you can see that when I put them together, maybe I should be consistent in how I do this. Okay, there we go. Now they fit a little nicer. So I've got 4, 3, and now I want 3 here instead. Oh, do I have a 1 by 1? There's no shortage of Lego in my house. Okay, here's what 4, 3, 3, 1 looks like. Okay, now what about over here? We want partitions of n into distinct odd parts. Okay, so what's an example of a partition of n into distinct odd parts? Well, distinct means I'm not allowed to have equal parts. Like this guy, not distinct. The two 3's are the same, but 3's odd, so hey, there's something going for it. Here's an example. Let's say 7, 3, 1. You don't have to have all the odd numbers, of course. You can skip, like I skipped 5, but you can't repeat anything. So 7, 3, 1, what does that look like? Well, unfortunately, there's no Lego that's a 7 by 1. They just don't make it. But you know what they do make? They make 4 by 1s. So let's just stack 2 4 by 1s together, because 7 is 2 times 4 minus 1. In fact, all odd numbers are twice something minus 1. So there's 7. And now 3, I do have 3's, but it's more fun to do it this way. So let's do it this way. So 3 is 2 times 2 minus 1. So I'll put my 3 right here. There's my 3. Okay, and 1, well, there's just 1, which is actually 2 minus 1. So there you go. So the claim of the theorem is the number of self-conjugate partitions of n is equal to the number of partitions of n into distinct odd parts. That's crazy. Think about why that might be the case. We definitely, when we have something that's like describing two sets, we really want a bijection between these two sets. That's sort of the proof from the book. So let's do an example just to convince ourselves, because we can fix n for this. So let's fix n to be something reasonable, like 8. And let's ask ourselves, how many partitions of 8 are there that are self-conjugate? Okay, so if I want a partition of 8 to be self-conjugate, what can I do? Well, it turns out that I know that we could have 4, 2, 1, 1, and we could have 3, 3, 2. And that's it. Now, how do I know that? Well, again, I'm going to think of building them this way. So what's the longest row length that I have? If I think about, could I have a row of length 5? If it's self-conjugate, could I start with a 5? So if I started with a 5, the problem is I would have to have 5 going up 2, and then that would be 5 plus 5 minus 1, which is 9. That's already too big. So 4 is the biggest I could have. So I could start with, 4 for a row, and then again, I have to do this trick, so it would look like this, okay? And now I've got 7, sorry. Yeah, so I start with a 4, and it looks like this. So now I've already used up 7 pieces, right? So I actually only get one more piece. So I can take this one piece and I can say, okay, well, here it is. There's that extra one piece that I get to use. So there's my composition. So it's not so exciting. Okay, so all right, that's the 4, 2, 1, 1, because 4, 2, 1, 1. Now, let's, instead of taking a hook of 4, let's take a shorter one like 3. 3 is nice and short. So if I take the row length 3, then it has to look like this. Now, how many studs have I already used up? I've used 5 studs. So I've got quite a few studs left. So let's see if I can put a big piece like this. This will give me 3 more studs, and I can just sort of nestle it in here. And that gives me the right number. Cool. So could I have done it a different way? Well, if I don't make the next row length 2, if I just make it length 1, then to be self-conjugate, I'd be done. So this would just have 5 plus 1, which would be 6. It would be self-conjugate, but it's not big enough. So that's it. These are my only 2 right there. And now we've depicted them right here. Okay. What about on the other side? Well, on the other side, I want partitions of 8 into distinct odd parts. That's actually much easier for me to come up with. Here's a big odd number, 7. That's the biggest odd number we could have, and we finish it off with 1 more. What else could I do? Well, I can't start with a 6. 6 is even. I could start with a 5, maybe. And then 5, what's left over? 3. I could put a 3 there. I can't put 5 and then a bunch of 1s, because I'm not allowed to repeat. And I can't put a 5 and a 2, because 2's not odd. Now, if I start with a 3, I'm completely and utterly screwed, because I can't put a number bigger than 3. So I'm going to need some more 3s or a bunch of 2s to get myself to 8. So that's it. There are only 2 of them. So the theorem looks true in this case. And now let's think about how to construct these guys. Let's see. I want 7, 1. So again, I don't really have, Lego doesn't make these odd ones for us. So I'll take this guy as 2. So this makes 7 because this was 4 and 4 minus 1. And somehow I am eternally running out of these 1 by 1s, but here's the 1. Okay, 7, 1. So I've made the 7, 1. Maybe I'll just put it here. Just, you know, no reason other than because it looks nice. So there's my 7, 1. And now, let's see, 5, 3. So 5 can be 3 plus 3 minus 1. The minus 1 because it overlaps. Minus 1 because it overlaps, you see. And now I need a 3, so instead of just grabbing another 3, because that would be way too easy, I'll take these two 2s and push them together. And there they are. So the question is, what is the bijection? And the answer is, well, let's see. Which way do we want to go first? Maybe we'll go this way. If you just unfold them, there, now they look the same. And here, if I just unfold these guys, now they look the same. These hooks are all odd length, right? Because I have overlap by 1, so I have twice a number minus 1. That's going to be odd. And they have to be distinct because, look, they have to be nested. Look what happens if I tried to put, so when I bend it back in, suppose I tried to take another 3 hook, which would look like this, and stick it inside here. Things are sticking over the edge. It's not a partition. It's not going to be weakly decreasing. There's a 3 and then a 4. That's not allowed. So definitely it has to go this way. So I fold everybody back up. Now I get my partitions again. And that's actually the proof. So the proof is, by example, by Lego, and we do the same thing here. You notice if I flatten this guy out, I've got that row. Flatten this guy out. Kick this piece away. And here's what we get. The same thing. So sometimes it's really helpful to think graphically and to picture what you're working with, because then a statement like this becomes very easy to prove. And you can look in the notes, and I've written down how the proof will go in words, so you can compare that, but I think visually it's much easier to understand.